Thrace Atlas just executed a maneuver that has completely shattered every prediction we had about its trajectory. The mysterious interstellar object that was supposed to be heading toward Earth has suddenly changed course and is now accelerating directly toward the Sun. This isn't a slight deviation or minor course adjustment. Atlas performed what orbital mechanics specialists are calling the most aggressive trajectory change ever observed from any object in space, natural or artificial. In less than 18 hours, Atlas altered its velocity by over $8,000 a meboni and rotated its trajectory by 47 degrees. That kind of maneuver requires thrust capabilities that dwarf anything humanity has ever built. But here's what has astronomers absolutely stunned. Atlas isn't just moving toward the Sun, it's diving toward it on a collision course that will take it deep into the solar atmosphere, far closer than any spacecraft has ever ventured. Current projections show Atlas will reach the Sun's chromosphere in approximately 12 days, plunging into regions where temperatures exceed 500,000 degrees. Natural objects don't suddenly reverse course and accelerate towards stars. Comets can't generate the thrust needed for this kind of trajectory change. What we're watching isn't astronomy anymore. It's witnessing technology in action on a scale that makes our most advanced spacecraft look like toys. The question isn't whether Atlas can change direction anymore. We just watched it happen. The question is, what's at the Sun that's important enough for Atlas to risk diving into a stellar furnace? Let's break down exactly what Atlas did, because the physics of this maneuver are absolutely staggering and reveal capabilities that rewrite our understanding of what this object really is. Multiple tracking stations detected Atlas beginning its trajectory change over an 18-hour period. The maneuver started with a series of intense thrust burns lasting approximately 47 minutes each, with 2-hour intervals between burns. This wasn't a single course correction. This was a carefully orchestrated sequence of powered maneuvers. An orbital mechanics specialist described what the data shows. Atlas executed what we call a multi-burn trajectory modification. Each thrust burn adjusted velocity and direction incrementally, building toward the final course change. That's advanced spaceflight technique, exactly how we'd program a spacecraft to perform major trajectory modifications efficiently. The total velocity change, what space engineers call delta V, was approximately 8,000 km. To put that in perspective, that's more than the escape velocity needed to leave Earth entirely. Atlas just demonstrated it can generate thrust equivalent to launching from Earth's surface to interplanetary space, while already moving at interstellar velocities. The energy requirements are mind-boggling. Conservative calculations suggest Atlas expended energy equivalent to the total power output of every nuclear reactor on Earth running continuously for 6 months, all in just 18 hours of thrust burns. Whatever propulsion system Atlas uses, it operates at energy densities and efficiencies we can't even theoretically match. But it's not just the amount of thrust that's extraordinary, it's the precision. Atlas didn't just blast engines and hope for the best. The thrust burns were timed and calibrated to achieve a specific final trajectory with incredible accuracy. The resulting course takes Atlas exactly where it apparently wants to go, straight toward the Sun. Radio telescopes detected something else during the maneuver. Electromagnetic emissions from Atlas spiked dramatically during each thrust burn. The signal characteristics match theoretical predictions for plasma exhaust from advanced ion drives or even antimatter propulsion systems. Whatever's pushing Atlas generates massive electromagnetic signatures as a byproduct. A propulsion engineer analyzing the emissions described them as extraordinary. The electromagnetic spectrum during thrust burns shows ionized particles accelerated to significant fractions of light speed. That's exhaust velocity approaching relativistic ranges. We can't build engines that do this. Atlas has propulsion technology decades, possibly centuries beyond our current capabilities. The trajectory change also required Atlas to overcome its own momentum. Objects moving through space tend to stay on their current path unless acted upon by external forces. To change course as dramatically as Atlas did requires not just forward thrust, but the ability to redirect that thrust vectorially, pointing engines in precise directions to modify both speed and heading simultaneously. Atlas's new trajectory is what's really got scientists both fascinated and terrified. This isn't a gentle approach to the Sun's outer regions. This is a dive toward the solar interior that should be suicidal for any known object or technology. Current tracking data shows Atlas will reach what's called the chromosphere, the lower layer of the Sun's atmosphere, in approximately 12 days. The chromosphere sits just above the Sun's visible surface and has temperatures ranging from 6,000 to 20,000 degrees C. That's hot enough to vaporize any spacecraft we've ever built in seconds. But Atlas's trajectory takes it even deeper. If the current course holds, Atlas will pass through the chromosphere and enter the Sun's photosphere, the layer we see as the Sun's surface. Temperatures there reach 5,500 degrees, and the density of solar material is thousands of times greater than anything in interplanetary space. An astrophysicist analyzing the trajectory described it as unprecedented. No spacecraft has ever ventured this close to the Sun. The Parker Solar Probe, our closest approach to date, reaches the outer corona, but stays well away from the chromosphere. Atlas is heading into regions where we've never had direct observations because nothing survives there. The closest approach point, called perihelion, will bring Atlas to within approximately 500,000 miles of the Sun's center. That's roughly 200,000 miles closer than Mercury's orbit and deep into the Sun's lower atmosphere. At that distance, solar radiation intensity is about 500 times stronger than at Earth's distance. But here's what makes this even more alarming. Atlas's trajectory shows it will slow down as it approaches the Sun. Normal objects accelerate as they fall toward massive bodies due to gravity. Atlas is apparently using thrust to brake its approach, which means it's not on a collision course. It's performing a controlled descent into the solar atmosphere. A trajectory analysis specialist explained the implications. When you brake approaching a massive object, you're either trying to achieve orbital insertion or you're planning to operate in that environment for an extended period. Atlas isn't just passing close to the Sun. It appears to be planning to stay there for a while. The approach angle is also significant. Atlas isn't diving straight toward the Sun's center. It's approaching at an angle that will take it through specific regions of the solar atmosphere, areas where solar activity is currently most intense. It's as if Atlas calculated its approach to maximize exposure to active solar phenomena. Multiple space agencies are now redirecting solar observatories to track Atlas's approach. The Solar Dynamics Observatory and other sun-watching spacecraft are being reprogrammed to focus on Atlas's path. Scientists worldwide want to observe what happens when an object demonstrating impossible capabilities dives toward the Sun. The obvious question is, what could possibly be at the Sun that's worth this kind of risk? Several theories are emerging, each more extraordinary than the last. The most straightforward explanation is energy collection, but on a scale far beyond what we observed during Atlas's previous corona passage. If Atlas can survive in the Sun's lower atmosphere for extended periods, it could harvest stellar energy directly from the densest regions of solar material, providing power reserves orders of magnitude greater than before. A fusion energy researcher described the potential. The Sun's chromosphere and photosphere contain energy densities we can barely imagine. If Atlas has technology to tap into those regions directly, it could collect energy that would power advanced systems for years, decades, possibly longer. It's the ultimate refueling station. But there's a more speculative theory that some scientists find compelling. Atlas might be attempting to communicate or interact with the Sun itself. Recent observations have shown the Sun has complex magnetic field structures, plasma dynamics, and behaviors we still don't fully understand. What if Atlas is equipped to study or even influence solar processes? An astrophysicist raised the unsettling possibility. We think of the Sun as a giant fusion reactor, but it's also the most complex magnetic and plasma system in our solar system. If Atlas has technology to manipulate magnetic fields at the scales we've seen, it might be able to interact with solar dynamics in ways we haven't considered. That's either incredible science or a potential weapon, depending on how it's used. There's also a more alarming theory. Atlas might be attempting to modify the Sun. Sounds like science fiction, but consider what we've observed. Atlas has demonstrated technology far beyond ours. It's diving toward regions of the Sun where it could potentially affect solar processes. Even minor influences on solar dynamics could have massive effects on the entire solar system. A solar physicist explained the nightmare scenario. The sun operates in a delicate balance: fusion rates, convection patterns, magnetic field cycles. If something could disrupt that balance even slightly, the effects would propagate throughout the solar system,